Yeah. Hello guys. So we are left with the last two types of the strip lines. They are coplanar and the shielded one. So we'll see the coplanar first. The coplanar means it is on the same plane, I can say. Yeah. So there is always strips as well as there is a dielectric material, right? So this is the dielectric material that we are placed. It's of thickness D, and the two strips here we are using two strips, and those two strips are placed on the same plane, we can say. So here the width of the plate is considered as, strips are considered as W, and the distance between the two strips is considered as S. One of the plate, because we need a ground connection, so we normally one of the plate here it is connected to the ground. What is the benefit of this? Why we need this coplanar strip line is whenever it is our parallel strip line. On parallel strip line, on both the tops, one was on the top, the other strip was on the bottom. Here the shunt connection was difficult, so when it is on the same plane, the coplanar as in coplanar strip lines, the shunt connection is easy, and this is one of the advantage of coplanar. It helps in the microwave integrated circuit designs. So because of this, what happens, the reliability it increases, as well as we can see the reproducibility is also enhanced, and the production cost will reduce in case of our coplanar strip lines. So as I have told, it has dielectric material, and here there as in parallel we have two strips, but both the strips are on the same plane, and one of the strip is connected to the ground. This is the design that you should remember for the theory explanation. Along with this, as we have seen in the other strip lines, we have to compute, we want what is the characteristic impedance. The characteristic impedance of the coplanar strip line is given by, it is Z0 is equal to 2 times P average divided by I naught square. This is something like our average power equation. Power equation is what? Power equation is nothing but current square, it's current square divided by into R, right? This expression we have already seen. And what is the current? It is the RMS value of the current that we are considering. So it is Im peak value divided by root 2 its square into R. So what happens? It is Im square divided by 2 into R. So if I rearrange this, the resistance is given by, it's 2 times P divided by it's Im square. It's the same expression. In place of R, it is the impedance we are speaking. So it is Z0 is equal to 2 times P average divided by I naught square. So from this I can say what is our I naught? I naught is nothing but the total peak current. I naught is the total peak current. And what else? The other thing what is given here is the P average. What is the power average? The power average that is flowing in the positive in any direction, because whenever we speak about the radiations or about the power here, we speak it's depending on the coordinate system. So X coordinate, Y coordinate and Z coordinate. So here the expression for power average is given, it is along the Z direction, that is given by half of the real part of, it's a double integration, it is E cross H, it is the cross product that we are computing, dot A Z bar dz, dx dy. Yeah, we are speaking about the power over here. So when we speak about the power is given by power density into area. And in our, I guess you guys are remember that power density is nothing but the this is the expression that can be derived from our Poynting theorem, right? So this is, if I say this is along the x and if this is along the y, then we can say it is half of real part. We are speaking about only the real part, so half of real part of double integration, it is Ex, I'm considering into Hy, it's a complex conjugate, dot Az bar dx dy. Why it is dx dy? Because we are considering the electric field intensity in the positive x direction, and hy, that is the magnitude of the field intensity in the positive y direction. So we are speaking about x and y. That means if we are considering it in that direction, then the area is given by this area. Unit vector will always be perpendicular to the area. If x and y are the x and y, yeah, this you can say it is in the x direction, and this the field in the y direction. Magnetic field, if we imagine it is in this direction and the electric field is in this direction, then what happens? The area what I have to consider, the strip, if I am speaking, I can say the strip is given by, this will be our dx, this will be our dx, and this will be our this will be our dx and this will be our dy. So total area is given by dx into dy, and always, as I told, the unit vector should be considered perpendicular to this area. So what happens, the average power what we are speaking, that will be also along the z direction. So remember this, guys, this equation is from our Poynting theorem. Yeah, so that's it about the coplanar strip lines, only so much. Usually if it is asked, they will ask you to explain coplanar strip lines or write a note on coplanar. Usually they ask the coplanar and the shielded strip lines together, because it's a very small theory part that you have to write here, right? So it's usually asked along with the shielded strip lines, something like for 6 marks or so, so that 3 marks for this coplanar and 3 marks for the shielded. Even shielded also nothing much has been explained here. So the next topic we'll see about the shielded strip lines. Yeah, so as I told, the last type of strip line is the shielded strip line. The shielded strip line, we have the dielectric substrate like this, and here the strip is placed at the center. The strip is placed at the center. 1 second, guys. Yeah. Then what about the upper and bottom of this dielectric? The top and the bottom of the dielectric, we place the ground plates. And these ground plates are not interconnected here, they are separate. Yeah. Okay, so here is the strip. Here the center one, as I have told, this is our strip and it is immersed, it is inside the dielectric. Let I can say the thickness of this, will consider it as T, and the width of this, as we have considered previously, the width of the strip is considered as W. What next is required? The distance between the ground, I can say, or the the thickness of the dielectric substrate, we can call anything. So this will consider it as D, and let this be A. Anything, we'll just imagine it is A. Yeah, now in this what happens, and this area, it's a dielectric area, so I can show it like this. Yeah, now what about the fields here? Here there is a strip. Because of the strip, there will be the magnetic field as well as there will be a dielectric field, right? Both types of fields will get, so we'll show both the fields. This is how the electric fields can be shown, because we know that electric fields, usually it starts from the positive and it ends at the negative. If there is no negative, that means we consider it ends at ground, right? So this is how the field will be, electric field will be. Then what about the magnetic field? The magnetic field, we can show it like this. Magnetic field will be in a circular motion, right? That we have already seen. So this is how around the plate we can show the magnetic field. what's the direction we can give? The direction can be given like this. Yeah. So it is in a circular motion, the magnetic field, and the electric field, as I shown, will be the lines which usually starts from the plates, because we consider if we speak that there are positive charges, and they will end at the negative charges. If no negative charges, it is infinity, or I can say it is the ground at which it ends, right? So this is how the conduction we can show, or how the magnetic field and the electric fields can be shown in a shielded strip lines. Now what happens, what type of propagation is here? The propagation is a transverse electromagnetic, because if we speak about this is the direction that we are considering of the plate, then the field will be perpendicular to the transverse towards the direction of propagation, right? Both the fields, the magnetic field as well as the electric field, both are perpendicular to them. So if they are perpendicular, means we say that it is a transverse electromagnetic, both electric as well as the magnetic. So it is the TEM mode. The different types of modes I had already explained in all the previous videos. Yeah. Now what happens at the edges of the field? At the edges of the fields, you can see it is not that all the electric fields starts from the plate and it ends at the this one, ground plate, right? There are some fields which is like this also, which is going to this, and where there is no ground connection also, which is like, yeah, it is searching for the infinity and it is going to infinity, what we can say. And these types of fields are called as fringing field lines. Guys, remember these type of fields, which is not it is not that all the fields whatever has been started here, it's not ending at the ground plate. There are still more field lines which is like going to infinity, what we can say, and these field lines are called as the fringing field lines. This type of property, even this happens in the capacitors also, we can say. You just imagine, guys, capacitors, you have two plates here, and what happens, the field in the dielectric medium, the charge motion, or we can say it is the field that occurs between these two. It's not that all the fields will be like this, from the positive to the negative or something. There will be some fields which will be like this also, which is going away from this, right? And those are nothing but our fringing field lines. These are called as the fringing field lines. Now if the dimension what we have considered, if that d is less than the half of the wavelength, if d is smaller than half of the wavelength, then what happens is that transverse direction of propagation cannot propagate in that direction. So, and there will be an attenuation, and the attenuation will be exponential. Like it will be shown that the attenuation of the signal will be attenuation, in the sense we consider it is decreasing, right? So the power, or we can amplitude or power, whatever, whichever content you want, you can use that will be a decreasing power, or we can say it is about the signal also. Both the things have the same meaning here. Now again, what we have to do here, again we have to write the characteristic impedance expression, and before that we'll see what type of dielectric materials are used here. Either the dielectric material can be of Teflon, or it can be of polyfine or polystyrene. These are the different types of material, the dielectric material that can be used in a shielded strip line. So that's it about the explanation for the shielded strip line. The only thing we are left with the characteristic impedance. So what is the characteristic impedance given by? The characteristic impedance expression is given as Z0 is equal to 94.15. They give no derivation is given directly. Remember this expression, which you may need for the problems. So W divided by, it is D, K, capital K, it's a capital K here, plus CF, which is the fringing capacitance, 8.854 epsilon r whole power minus 1, and this is the characteristic impedance of a wide strip. When it is a wide strip, we say W by D is very much greater than 0.35. W by D is very much greater than 0.35. This is the condition that we are considering for the characteristic impedance expression what we are writing. There is some other equation also which when it is less, which is not required, we'll consider only this. So as I told, the expression is 94.15 divided by root of epsilon r into its W divided by D. It's a capital K and it's a constant, and what is that we'll see, plus CF divided by 8.854 into epsilon r, where K is 1 by 1 minus T divided by D. K is 1 by 1 minus T divided by D, where we know that T is what? T is the thickness of the strip, right, that we had already considered. Thickness of the strip, you can see in the diagram, even in the diagram we have considered the thickness of the strip as T. What next in that expression? The next thing is D. What is D? D is the distance between the two ground plates, we can say, or it is the thickness of the substrate, we can say. Anyhow, we can name that a distance between the plates or so on. Now what next? The last thing is about CF. What is CF? As I have told, it is the fringing capacitance, and this fringe capacitance is given by, this is a bit lengthy equation. It's 8.854 epsilon r divided by its pi into its 2k ln of k plus 1 minus k minus 1 ln of its k square minus 1. Yeah, this is the equation that you have to remember. It's 8.854 epsilon r divided by pi into 2 k ln of k plus 1 minus k minus 1 ln of k square minus 1 picofarad per meter. So this is the fringe capacitance given. So that's all about the different types of strip lines here. We have seen all the types of strip lines here, starting from micro strip line, and then what we had seen was about the parallel strip line, and next was the coplanar and the shielded. So in case of our micro strip line, what we had seen, I'll just brief the things whatever we had seen in micro strip line, about its design, I can say, design or construction, we can call it as a construction, its construction, and then about the radiation also, which is very important, the radiation pattern. And don't get confused with the antenna radiation, but it is how the magnetic field and the electric fields are transferring, that's it. Next we had seen about the characteristic impedance, the expression we have derived for the characteristic impedance, and then in the microstrip lines we have gone through, or we have seen the last topic was about the losses. There are different types of losses that we had seen. One was the ohmic loss. The next was the what was the next topic that we had seen here after ohmic loss? Then it was the dielectric loss, and the last one was the radiation loss. Yeah, so that's all about the microstrip line what we had seen. And the next topic that we have gone through, it was about and here one more topic that we had seen, that was related to the quality factor of the microstrip. Yeah, the next was the parallel strip line. In parallel strip line we have seen the characteristic impedance, and then we have seen about the losses. Here mainly we had did the ohmic losses and the dielectric losses, alpha and alpha, the expressions that we have seen, the attenuations, right? Yeah, so that's all about the parallel strip line. The next what we had seen is about the coplanar strip lines. In coplanar strip lines, it's just about its construction. Even for parallel also there is its construction, and after construction just we had seen only the expression of z naught, that's it. Last one is the shielded one. Shielded strip lines. In shielded strip lines, again it is a construction and the characteristic impedance expression. Yeah, that's it. So coplanar, this is how on the same plane, it's easy to remember. Only microstrip line, it has only single strip on the dielectric slab. Parallel means the strips are parallel, there are two strips, and coplanar means on the same plane there are two strips, and the last one is the shielded, it's covered, I can say. So it's placed inside the dielectric, somewhere at the center of the dielectric. This is how the constructions can be remembered, and for all these topics we have seen a lot of expressions, right? So we didn't see any problems. In the next class on Monday, I want both the classes together. We'll discuss on the problems till of this chapter, all the strip line problems left. It's like we didn't start with any of the problems, so we'll discuss on all the problems starting from microstrip line till this shielded strip line. Yeah, thank you guys.